Okay, so this is the beginning of Unit 7. Okay, so Unit 7. There's only 2 more units left, guys. Oh, it's fine. Do what? This one is not that long, actually. Unit 8 is quite lengthy. Okay, so differential equations. We've been working with differential equations all year because a differential equation is an equation that contains a derivative. So anytime you wrote down dy dx, that's a differential equation. All right, so we have something called a slope field. When I took calculus a long time ago, this wasn't a thing. All right, but slope fields, I think it came around 2003 was the first time. I don't know. I don't know. I'm not sure. Good question. But I went back and looked. Like in my old calculus textbook, I still have my high school calculus textbook. Okay, it wasn't in there. And I think I started reading about it in the early 2000s was the first year it appeared on the exam. Okay, so, or at least maybe it was a thing, it just wasn't tested as part of the AP calculus curriculum. Okay, so a slope field is a graphical representation of the solution to a differential equation. Okay, and we're starting this unit with slope fields because we can create a slope field without actually solving the differential equation. Okay, so we're going to start by just kind of using slope fields to get a visual picture of what our solution curves look like. Then you'll transition into actually solving for those solutions. All right. So guys, the differential equation, what is a derivative graphically? Slope of a tangent line, slope at a point, right? So the derivative, the differential equation, gives us the slope, gives us the value of the slope at any point xy. So we can use that piece of information to draw tiny little pieces of these tangent lines at many points. Okay, so if we repeat that process many, many, many times, okay, you'll start getting a visual idea of what the solution curves look like. And guys, so that's called a slope field. So the idea behind a slope field is to make a graphical representation of the slope of a function at various points in a plane. And then if we do it at many, many points, you can start seeing what the solution curves look like. All right. So let's look at this differential equation. So it says dy dx. Okay, so remember, dy dx tells us the slope at a point. So the slope at any point is going to be the x-coordinate minus the y-coordinate. So we are going to calculate the slopes at these points and then use that information to sketch a little piece of this slope field. All right, so guys, we just have to follow the formula. So the first one's done for us. At the point -1, -1, the formula says take the x-coordinate, subtract the y-coordinate. So -1, take away -1, 0. So now I'm going to come down here to this coordinate plane and find that point, -1, -1, and draw a tiny little line segment with a slope of 0. So -1, -1. All right, let's look at the next point. So xy, 0, -1. Why is this shaking? So it says take the value of take the x-coordinate, subtract the y-coordinate. So 0, take away -1. What does that give us? 1. All right, so let's go find this point. 0, -1. All right, so if you are asked to draw a slope field on the AP exam, they'll tell you it's usually 9 points or 12 points. And they're not going to we don't take out a ruler and measure and make sure your slope of 1 is exactly 1. But they do look at relative steepness. It's typically 2 points. 1 point for the 0 slopes. So they want to see nice horizontal tangent lines at those points where the slope is 0. And then the others, they compare the relative steepness. So you want to make sure your negative slopes are clearly negative and your positive slopes are clearly positive, and a slope of 2 is steeper than a slope of 1. All right, so at this point right here, 0, -1, we got a slope of 1. Is that right? So guys, if I was drawing a line with a slope of 1, and I started at this point, okay, I would go up vertically 1 and horizontally to the right 1. So I'd have a line connecting these 2 points, right, that pass through those 2 points. So I kind of visualize that line in my head, and then I just draw a little piece of it. All right, so next point, dy dx, we take the value of x and take away the value of y. So 1 minus a negative 1, 2. So the point 1, negative 1. So right here, I'd have a slope of 2. So I kind of like picture, if I was drawing a line with a slope of 2, I'd go up 2 over 1. So if there's a point right here and I try to draw a line, just make sure that it's steeper than the slope of 1. All right. Let's keep going. Negative 1, 0. So take the value of x, subtract the value of y. So negative 1. So at the point negative 1, 0, we have a slope of negative 1. So a slope of negative 1 would be a line that passes through these 2 points. All right, 0, 0. What would be the slope of the point 0, 0? 0 minus 0. Right there through the origin, have a little horizontal tangent. Point 1, 0, dy dx. The value of x, take away the value of y. So at that point right there, have a slope of 1. So I want to remember that this is a slope of 1 and kind of make sure those have very similar slopes. All right, let's do these last 3 points. All right, what is negative 1 take away 1? All right, I'm just going to calculate these 3 slopes real quick. So 0, the x-coordinate, take away the y-coordinate. So 0 minus 1, negative 1. And the point 1, 1, 1, minus 1, 0. So a slope of negative 2, so I imagine a line that passes through these 2 points. And just draw a little piece of it. For this point, I would imagine a line that passes through those 2 points. Draw a little piece of it. And then here, another slope of 0. Now we're only looking at 9 points, so we don't really see the solution curve starting to form with such a small slope field. But this is what could be asked of you on the AP exam because they are time consuming to draw. It's typically 9 or 12 points. So you got to make sure your 0 slopes are in the right spot, and then the steepness of the other slopes are fairly accurate. Everybody okay with creating a slope field? All right, so look at the next page. At your tables, do these first 2. Just do 1 and 2 at your tables.
Question.
Yep. Mm-hmm. Okay, start doing it, and you'll realize that you won't need as much time as you think you do. See if you figure out a way to do it quickly. See, look at that. It won't take you as long as you thought, right? So what do you notice about all those points? I would, like, if I pick a point down here, I'd have to go 1, 2, 3, 1 to kind of visualize a line passing. Just make sure they're steeper than the 2 slopes.
So if you got this point that's at, what'd you say, 2? So if I'm at 2, 0, you plug in 2 here, you get 3. So your slope is 3. So then if you go to 2, 1, what's your x value? Plug it in, what do you get?
about this right here?
I'm just wrapping my head around. My brain is putting the puzzle pieces together.
Okay.
I'm almost there.
Okay.
Once I place it, it'll correct.
So look at this. So the slope at every point only depends on the x-coordinate. Here it was time-consuming because the derivative depended on both x and y. Here, all I need is the x-coordinate.
Okay.
So see all these points?
Mm-hmm.
They have the same x-coordinate,
Okay.
so they will have the same slope.
I see what you mean.
See all these points? Same x-coordinate, same slope. Okay.
Makes sense.
So do the next one. So now this one only depends on the y-coordinate. Hold on.
It looks like you're looking at something in a microscope. When you shake it off, forget the memory. Yesterday. Oh, that's so funny. Yesterday for a mock AP lit test, one of the poems we had to write an essay over was about sheep.
Wow.
And
Okay.
how it connects to life. And how it helps you remember your dead dad. That's how the dude. So glad I teach math.
I know, right?
And then literally like the last one for the first stanza. And then our second one was an octopus that was like.
And the octopus was an allegory for the birth of Jesus Christ.
Oh,
I never heard my pastor say.
So whenever if dy dx is a negative number, we're down.
Okay. Okay, so when I asked you to draw these slope fields, some of you got a little nervous thinking, how much time do we have? But then realized that it might not take you as long as you thought. Okay, so what did we notice about number 1? As the previous one? Okay, so yeah, this one is a derivative, okay, a slope that only depends on the x-coordinate. So along every vertical line, all the points have the same x value, so all the points will have the same slope. So once you figure out the slope at any point for a particular x value, you can just draw the rest the same, yes? Okay, so then on number 2, I haven't drawn it, but everybody has a good slope field. So number 2, what did we notice? It only depends on the y-coordinate. So along every horizontal line, for example, this line y equals 0, we know that 2 times 0 is 0. Once I have the slope at one point on that line, I can draw the rest, and so on. Okay? Now, let's go back to number 1. This is a little bit larger slope field than on our first page. Can you start visualizing the solution curves? Like if I were to pick a point on this, you don't have to draw this, but if I were to pick a point, because sometimes on the AP exam, they'll give you a slope field, and then they'll give you a point, and they'll ask you to sketch a possible solution curve, okay, through that point. So what did you say it looks like? All right, so if I just chose this point, and I call it like riding the waves. I have to kind of like just take it go where it takes me. And she said it looks like a quadratic function. Well, think about this, guys. This is a differential equation that is what we call separable, and we could actually solve. Okay, this is prefacing your next lesson. But if I were to solve this, I would do what's called separating variables. I would just multiply both sides of the equation by dx. Then I would integrate both sides. The antiderivative of 1 with respect to with respect to y is y. What's the antiderivative of x with respect to x? X squared over 2, or 1/2 x squared, plus x, and then plus c. Guys, graphically, what does the C do? Moves it up or down. So if I chose a different point, it would just be this same graph, just translated up or down. Does that make sense? So we know that this is what our solution curves would look like, and we could see those quadratic formulas, those parabolas in that slope field. Good? All right. So when it becomes helpful is when we have a differential equation that we call not separable, meaning I can't use multiplication and division to separate variables and get all things y on one side and all things x on the other side. And so I could not solve this differential equation. But I can draw a slope field and get a visual idea of what the solution curves would look like. Okay? All right, is everybody comfortable drawing a slope field? Okay, sometimes it's time consuming, sometimes it's not as time consuming. All right, so then let's go on to different types of problems. All right, so this is what I was just showing you. If we sketch a curve connecting the slopes of a slope field, we get what's called a particular solution to the differential equation. Okay, so this is a slope field for the differential equation dy dx equals 2x. So how many functions share that derivative? How many functions have the same derivative, 2x? An infinite number. Okay, an infinite number. What's the antiderivative of 2x with respect to x? X squared plus c, right? So you can see all these quadratic functions that we could draw in there. The plus c, all it would do, shift things up vertically. What function has x squared as its derivative? Let me rephrase that question. What's the antiderivative of x squared? X cubed over 3. So if I were to pick a point here, let's say the origin, and I were to sketch my solution curve, kind of just like following these waves, do you see that cubic function forming? You see it, Devin? All right, so that is the purpose of a slope field, so that we can visualize the solution curves when sometimes they're not possible to find analytically. Okay? All right, so let's do some matching. We'll look at some. They don't have matching questions on the AP test, but they will either present you with a slope field and ask you to find the differential equation, or present you with a differential equation and have you find the slope field. Did you have a question? Okay, so let me talk you through this first set, and then you can do the second set. So look at this slope field in part A. Like, ignore these equations down here. What do you notice? There would be, yes. Okay, what else do you notice? So what I notice is, like, I can choose any horizontal line. Like, perhaps this is line y equals 1. All the slopes are the same. Okay, I can choose another horizontal line. All the slopes are the same. So what would that mean about my differential equation? There you go. So I would say dy dx only depends on y. Okay, that's one of the first things I notice on that one. Look at B. What do we notice about B? Okay, I see quadratics, nice. But I can also find any vertical line, right? So like this line x equals -2, or this line x equals 3, and all the slopes are the same. Okay, there you go. So we have a slope field, a differential equation that only depends on y. Yep, yes, thank you. Only depends on the x coordinate. All right, what do we notice on C? Okay, same thing. I can find any vertical line, so any x equals line, all the slopes are the same. So again, we have a differential equation that only depends on the x coordinate. Now what about D? Okay. Because if I look at a horizontal line, I see many different slopes, right? If I pick a vertical line, I see many different slopes. So that tells me that we're going to end up with a differential equation. dy dx depends on both x and y. And y. So we would have a differential equation in terms of both x and y. All right, so let's see if that helps us match up. So what would go with, which differential equation goes with A? 3, because I only have one differential equation that depends on y only. So this would be A. D is the only one that depends on both x and y. So D would have to be matched with 2. All right, so when we looked at B, somebody said they see quadratic functions. Okay. So which one? If we start with a quadratic function, the derivative of any quadratic is linear, right? So B goes with which one? 4. So then, by default, number 1 has to be C. But what do you see when you look at? Okay, so we actually see the antiderivative of sine, which would be negative cosine. So we can draw in some negative cosine curves in there. Everybody good there? All right, move on to this next set. Talk to each other. So can you look at this and kind of see that this one's going to depend on both x and y. This one slopes along a vertical line. So at all these points with a common x coordinate, we have a common slope. So then this one will depend only on x. So here, along any line, we're on the y coordinates. There you go. So now we got to figure out a way to check these two. They're both in terms of x and y. So which one goes with which? So how did you figure out the between 3 and 4? Okay.
I just plugged in a random number. It's
how to determine these two. Okay, so you picked a point, plugged it in.
Here? Right back? Okay. Okay. Very good. And it was related to the US Central. When they're both
Yes.
positive, the slope is negative. When they're both negative, the slope is negative. When they're opposite, the slope should be positive.
Okay, so everybody has the right answers, and everybody had a slightly different strategy. Okay, which is fine. Okay, so this is what I saw, so I just copied it down. A lot of y'all were saying this is x and y, this is just x, this is y, this is x and y. Okay, so we were okay with number 1 being b and number 2 being c. So then we had two differential equations in terms of both x and y. Two slope fields in terms of both x and y. So now I had to do some sort of thinking and problem solving to figure out which is which. What was your strategy, Cameron? So he picked a point. Okay, he picked a point off this graph, plugged it in, it worked. So that's how he decided. What did y'all do? Similar, plugged in a point. Okay. So what do we know about all the points in the first quadrant? Positive x, positive y. So when I take a ratio of positive over positive, okay, we get a positive, the opposite would be negative. So do we see all the slopes in the first quadrant are negative? Okay, what do we know about points in the second quadrant? X is negative, y is positive. If I take that ratio of x over y, we get a negative. The opposite of that is positive. Do we see all the slopes in the second quadrant are positive? Okay, so that was y'all's strategy, right? Another way, what I like to look at is I like to find the zero slopes. Sometimes this works, okay? The first thing I do is figure out, is it in terms of x, y, or both? Then I look for zero slopes. Then I check points like this using the sign of x and y. And then if all else fails, if I'm still stuck, I plug in a point. Because we got to do things as efficiently as possible on a time test. Okay, so look at this. See these zero slopes? See where all my zero slopes line up? And that appears to be the line when y is equal to the opposite of x. So think about this. If I set this equal to 0, that's y equals the opposite of x. So along that line, y equals negative x, I see all those zero slopes. Over here, where do we see the zero slopes? At every point where the x-coordinate is 0. So think about a fraction with a numerator of 0. 0 divided by 1 is 0. 0 divided by 2 is 0. So that's how I would decide between these two. So there we go. We have multiple strategies. Everybody okay with that? Okay. Look at this next example. What do you know? What's different about this, guys? We don't have dy dx, okay? So we just practiced taking a slope field and matching it to its corresponding differential equation. Now we're taking a slope field and matching it to the solution of the differential equation. So you have to remind yourself, what does a slope field tell us? Okay, what does it provide for us? It provides that graphical representation of a solution curve. So what I could do is I could pick a point here, kind of like draw myself a solution curve, see what we're working with. And then I ask myself, okay, what function type does that appear to be? Does that look like a quadratic? Mm-mm. Does it look like an increasing exponential function? Does it look like a decreasing exponential function? But it's not exponential. Okay, so we know what this one looks like, right? We know a quadratic looks like this. Our e to the x function looks like this. E to the opposite of x would be that decreasing exponential. And what does natural log look like? It's the inverse of this one, so it's a reflection of e to the x over the line. Y equals x. So that's funny, actually. Okay, so do you see the difference? You got to pay attention. Am I matching the slope field to the corresponding differential equation, or are we matching the slope field to the actual solution? Okay. So if you're matching it to y equals something, you got to identify what function type you're looking at. Because there's a u in the word quadratic? Okay. All right. So somebody asked, okay, what does this look like, okay, on the AP test? So let's look at these two questions. Okay, so these are examples. You can tell it's kind of like I took a picture of the AP exam. All right, so we are looking at a slope field. We are looking at a slope field. They tell us the differential equation. It says if y equals g is the solution with this initial condition. Okay, so initial condition is the point -2, -1. What quadrant is that point in? 3. So somewhere -2, -1, so somewhere in this area. So if we took the limit as x approaches infinity of the solution curve, okay, of g, because it says g is the solution to the differential equation. So if we took the limit as x goes to infinity of that solution, what would it yield? So I'm a visual person. What I would do is I'd kind of just give myself a sketch. What does this solution look like if my initial condition is in this quadrant? So I kind of just ride the waves. Here. And guys, it won't cross over a horizontal asymptote. It also won't cross over a discontinuity. The solution to a differential equation will be a function. So guys, looking at this sketch of our solution curve, what is the limit as x goes to infinity? There you go, 0. So guys, if my initial condition was in quadrant 3, I would have a different answer, because that curve would approach that y equals 2 horizontal asymptote. Okay, so you got to find that point, find the initial condition. Okay, because my answer would be different if we had a different initial condition. Everybody okay there? All right. Look at this next example, and I'm going to give you a couple minutes. Y'all can talk to each other. Matching the slope field to the corresponding differential equation, not the solution curve. I thought I heard you say, if you see something quadratic, so you think there has to be some sort of quadratic involved. I would narrow it down to 2 answers. The first one that I would eliminate is E. Why would I eliminate E? Right, and I can clearly see that that's a function of both x and y. do you think it's that? So you plug in 1 point, and you got the right slope. What if that 1 point gave you the right slope on every one of those? So you took 1 point, the same point, and used it for all of them? I would focus on the zero slopes. Focus on the zero slopes. Where do I have zero slopes, and which differential equation would provide those zero slopes?
Yeah. He was listening to your explanation, which was very good.
But that would also it could be also. You're right.
We'll go.
I was right. Stop trying to say yes. Say right.
Okay, so guys, remember on a question like this, okay, this is on the multiple choice non-calculator, so you have an average of 2 minutes per question. So if it's taking you any longer than that, you're gonna want to skip it, yeah, and move on. Okay, but remember, you've only done this for 30 minutes. It just takes practice. Okay. So the first thing, what is one differential equation we can eliminate right away without question? Okay, E, because we can look at this slope field. I can see along any vertical line, any horizontal line, I have different slopes. All right, so E's out. So that's the first thing I do. I decide if it's a function of X, function of Y, or both. All right, so we're down to 4. The next thing I do is I find my zero slopes. All right, so based on how my y-axis is scaled with 3 up here, I know this is the line y equals 1. You with me? And then I can clearly see all the points on the x-axis have slopes of 0. So that's the line x equals 0. So that you got to be careful the way the axis is scaled. So 3 is here, so this is 1/2, 1, 1.5, 2, 2.5, 3. Okay. You got to be careful with that. Okay, so I'm going to set these equal to 0 and factor. How does this factor? Y minus 1. So think about this, guys. This would give me 0 at x equals 0. It would also give me 0 when y equals 1. So A is still in the running. Okay. What about B? If I set this equal to 0 and factor, so y plus 1 equals 0 at y equals negative 1. So if that were my answer, I would expect to see 0 slopes along the line y equals negative 1, which is not the case. So B's out. What about C? Where would I need to see 0 slopes on C? Y equals x squared, so I would need to see some pattern of 0 slopes along some quadratic function. So that one's out. All right, but here, if I set this equal to 0, I would get 0 slopes at y equals 1 and at x equals 0. So now we've narrowed it down to 2. So where do I go from there? So remember, the first thing I do is, okay, here's what I would do. I would choose a point in the third quadrant because I can see in the third quadrant all my slopes are positive. I know that in the third quadrant, I have negative x coordinates, negative y coordinates. So if I substitute that here, I would have a negative times a negative, which yields positive. But if I substitute it here, I would have a negative times a negative squared, which is positive, so I would expect to see negative slopes in the third quadrant. So D's out, A's our answer. Thank you. Sorry, I gotta pay attention to the time.